3.2 practice problems. The first problem here says the ionic compounds sodium chloride and magnesium sulfide are represented by the diagrams above. Which statement correctly identifies diagram 1 and identifies the compound with a lower melting point and explains why? So when I look at between diagram 1 and diagram 2, I'm going to first identify the relative size comparisons between the represented atoms here. So I have between sodium and magnesium. Magnesium is going to be smaller than that of sodium since it is a cation that has lost 2 electrons, so it is going to shrink down more. So with the darker circles being for our cation and our larger circles being for our anion, I'm going to go ahead and say that diagram 2 is going to be for magnesium sulfide, meaning that diagram 1 is going to be for sodium chloride. So I'm going to go ahead and eliminate the choices that disagree with me there, and I'm going to look between choice A and choice B here when we are talking about the relative lower melting point. Now, knowing what I know about melting points, they are going to be based off of the overall attraction between the complex, and that is going to come from Coulombic attraction. Coulombic attraction is going to be greater for that of magnesium sulfide, so we have a greater Coulombic attraction. Because we are going to have a greater charge differential, and then also magnesium is going to be smaller. So I'm going to look for the answer choice that reflects that as well. So A says diagram 1, it represents sodium chloride and has a lower melting point than magnesium sulfide. So far, so good. Has because of the Coulombic attractions between the singly charged sodium and chlorine ions are stronger. That is incorrect. They are weaker than that of the magnesium to sulfur charges because they have a lower charge differential and therefore have a lower Coulombic attraction. So I have chosen B as my answer. For number 2, it says a sample of a hard solid binary compound at room temperature did not conduct electricity. So things that do not conduct electricity when they are a solid, that is going to be covalent, ionic things, and then hydrogen bonds is not a type of compound. Metallic things do conduct electricity at a when they are solids at room temperature. But then it became highly conductive when dissolved in water. That is going to have to be ionic in nature because covalent compounds when dissolved in water do not make for good electrolytes, and electrolytes is my capacity to conduct electricity, whereas my ionic compounds are good electrolytes, and so this is going to have to be an ionic compound here. A student is given a sample of a pure white crystalline substance. Which of the following would be most useful in providing data to determine if something was an ionic compound? So things that let me know that this is probably ionic, we have high melting and boiling points. We're not going to conduct electricity when we are a solid, but we do conduct electricity when we are dissolved into water. So things like that are going to let me know that I'm dealing with ionic compounds. So I'm going to look for something along those lines. Examining the crystals of the substance under a microscope, covalent compounds can also form crystals, so that's not going to help me. Determining the density of the substance also does not help me. Covalent compounds and ionic compounds can both have varying densities, so not particularly helpful. Testing the electrical conductivity of the crystals. Again, both covalent and ionic compounds do not conduct electricity when they are in a solid state, so that is not going to differentiate this from a covalent compound. And then finally, testing the electrical conductivity of an aqueous solution of the substance means once I have dissolved it in water, seeing if it does conduct electricity at that time, and that is something that would make the ionic compound stand out from a covalent compound. So I'm going to choose that option. Based off of the diagram above, which of the following best explains why solid magnesium oxide is not able to conduct electricity, but liquid magnesium oxide is a good conductor of electricity? Solid magnesium oxide, we have it very constrained. My electrons are very much locked into their particular places. We are not able to conduct electricity as a solid because we cannot have those charges move about. And when we are a liquid, we are able to have those charges move about. You can see that we have a separation between the magnesium and the oxygen, this being the magnesium, this being the oxygen here, and that would allow electricity to flow through the substance, whereas here we have no break, no barrier, nothing to allow those electrons to go ahead and flow through. So I'm going to look for something that explains that. Magnesium solid does not contain free electrons, but magnesium oxides contain free electrons that can flow. This is not true. Magnesium oxide solid contains a water, but magnesium oxide liquid contains water and thus can conduct electricity. Actively, no. We can't see any water molecules in this representation. And then also remember that my conductivity of aqueous ionic compounds is going to come from the capacity to move the charges about, since I have separated cations and anions and I have space between those, not because of the water itself. Magnesium oxide solid consists of separate magnesium and oxide ions, but magnesium liquid contains molecules. Actively, no. Magnesium oxide solid consists of separate magnesium oxide ions and magnesium ions and oxide ions in a fixed lattice, but in the magnesium oxide liquid, the ions are free to move and conduct electricity. This is true. Them being fixed in a lattice, locked into a set shape, is why they cannot conduct electricity, whereas in the liquid state, they are more able to move about and are able to conduct electricity. Which of the following could be the identity of a white crystalline solid that exhibits the following properties? It melts at 320 degrees Celsius. This is a very high melting point. So I am probably going to be eliminating anything that is a covalent compound. So that would eliminate A. It does not conduct electricity as a solid. This would eliminate any metals. And then finally, it's going to conduct electricity in an aqueous solution. So between sodium hydroxide and silicon dioxide. Silicon dioxide, we have a lower electronegativity difference than between sodium and hydroxide ion. This is going to act more like a covalent compound, even though silicon is a metalloid, and therefore is kind of on the border for if it's going to behave like a metal or a nonmetal. But the electronegativity difference between silicon and oxygen is going to be a lot smaller than the electronegativity difference between sodium and hydroxide, where we have a full ionic compound here. So we are much more likely to be sodium hydroxide than we are to be silicon dioxide. The table above provides some information about two model types of steel, which are both alloys of iron and carbon. Which of the following best helps to explain why high carbon steel is more rigid than low carbon steel? So as a reminder, we have those carbon atoms, which are going to be very, very small. They are going to come in to our structure, and they are going to fill in those little small gaps in between my iron atoms, and thus are going to make it harder to bend because I just don't have as much flexibility because I have carbons junking up my iron here. So I'm going to look for something like that. Elemental carbon is harder than that of elemental iron. Actively no. Elemental carbon depends on the actual type of carbon that you have present, but we have lots of different carbon models, and they all have differing hardness levels. So you have on the softer end graphite that you will use in your pencils, which is very, very soft enough that it can rub off onto paper. And then on the harder end, you have diamonds, which are one of the hardest things that we can produce in the first place. But just because it's carbon doesn't mean that it's harder than iron, because it does very much depend on what the actual structure of those carbons are. So that's going to be eliminated. The additional carbon atoms within the alloy make high carbon steel less dense. No, it's going to make it more dense because more things are going to be inside of that same sample. The additional carbon atoms within the alloy increase the thermal conductivity of the high carbon steel. Carbon is not a good thermal conductor. Things that are good thermal conductors are metals, and carbon is actively not that. The additional carbon atoms within the alloy make it more difficult for the iron atoms to slide past one another. This is going to be my choice, and is going to be why it is going to be hard and brittle. Those carbon atoms are coming in and getting in between all of my iron atoms and are gunking up my pathways in which I can move, and thus making it more difficult for those iron atoms to slide past each other, which is what makes them more likely to snap instead of bend, which is what malleable and ductile things are. They are able to bend. Which statement best helps to explain the observation that ammonia, NH3 liquid, boils at negative 28 degrees Celsius, whereas PH3, or phosphorus trihydride, boils at negative 126 degrees Celsius. As a reminder, we are in the negatives, so this is lower than this. This is the higher boiling point here. And things with a higher boiling point have a stronger intermolecular force happening on those individual molecules. So dispersion forces in NH3 are weaker. We can immediately eliminate that. We are looking for those forces to be stronger. Then we have the dispersion forces of NH3 are stronger than that of the dipole-dipole forces. London dispersion forces are the weakest of the dispersion types, of the intermolecular force types, and they are definitely weaker than dipole-dipole. So that's going to not be true. Also, NH3 is going to be a polar molecule just like PH3. We are going to have some dipoles happening here. NH3 has hydrogen bonding that is stronger than the dipole-dipole forces of PH3. Hydrogen bonding can only take place between hydrogen, nitrogen, oxygen, and fluorine. Ammonia does, in fact, have all the necessary components, whereas PH3 does not. And so I would have hydrogen bonding here, and we do say that it is a stronger intermolecular force, so that is going to be my choice. D says that this is going to be weaker. That would mean that my boiling point was lower, so that doesn't make any sense. So C is going to be my choice because hydrogen bonding is available, and those intermolecular forces are stronger than that are represented in PH3. A certain crystalline substance that has a low melting point, does not conduct electricity in solution or when melted, is likely to be. So low melting points and not conducting electricity either in solution or as a solid, that is going to be a molecular solid. We are dealing with covalent bonds, but we are dealing with molecules here. A covalent network solid is not going to be the same as a molecular solid. We are definitely not metallic or ionic here, and we don't have any reason to say that this is a polymer versus a molecular solid. So I'm going to go ahead and say that this is a molecular solid. At room temperature, diatomic iodine is a molecular solid. Which of the following provides characteristics of diatomic iodine with the correct explanation? So we are diatomic, so we have two iodines bonding together. So we do not have a difference in electronegativity. And we have pretty strong intermolecular forces since we are staying as a solid at room temperature, versus if I had very weak intermolecular forces, I would be a gas or a liquid at room temperature. So having a high melting point because of weak intermolecular forces is going to be wrong, because if I have weak intermolecular forces, then that means I would have a low melting point. It is hard because it forms a three-dimensional covalent network that is not evidenced by the formula here. It is not a good conductor of electricity because its valence electrons are localized within bonding and non-bonding pairs. This is correct. We are a covalent compound here. We are not going to be able to conduct electricity because our valence electrons are locked into bonds. And then it is very soluble in water because its molecules are polar. That is actively not true. This is an actively non-polar molecule, so it is definitely not going to dissolve in water because of its polarity. The structure of one form of boron nitride is represented above. This form of boron nitride is one of the hardest substances known. Which of the following best explains why boron nitride is so hard? Okay, so as we are looking at this, it might be a little bit difficult for you to picture, but just try to like find a specific thing and then look and see if you can pop that out into a visual in your mind. Boron and nitrogen ions are held together by ionic bonds. Boron and nitrogen are going to have very similar electronegativities, so they are not going to be an ionic compound. Boron nitride is a network solid of atoms connected by covalent bonds with fixed bond angles. It is going to be a covalent compound, and we do have fixed bond angles, so I'm going to hold off on eliminating that until I see if we have a better choice. Boron nitride is an alloy. Alloys are typically harder than the elements used to make them. Alloys are mixes of metals, and neither boron nor nitrogen are metals, so this is not going to be an alloy. Boron nitride is a polymer made of long chains of boron atoms and nitrogen atoms held together by London dispersion forces. This is not a polymer. This is a network solid. Polymers are single things that kind of go off in very long chains. This is not a single thing that goes off in a very long chain. This is something that could repeat over and over again and is not going to be a polymer held together by London dispersion forces. Instead, I'm going to choose choice B, that it is a network solid of atoms connected by covalent bonds with fixed bond angles, for why it is going to be so hard. In solid methane, the forces between neighboring methane molecules, CH4 molecules, are best described as, so methane is going to be non-polar, so I'm going to get rid of anything that tells me anything else. So ionic bonds, definitely not, it's non-polar. Ion dipole means that I would have to be polar. Methane to methane is not going to be a covalent bond, and I'm left with hydrogen bonds or London dispersion forces between the two. Hydrogen bonds have to take place between hydrogen, nitrogen, and nitrogen, oxygen, and fluorine. I don't have nitrogen, oxygen, or fluorine present, so hydrogen bonds are not an option. So my only option left is going to be London dispersion forces. The best explanation for the fact that diamond is extremely hard is that diamond crystals are made up of atoms that are intrinsically hard because of their electronic structures. This is actively not true. Diamond is made of carbon. Carbon can have varying hardness levels depending on the environment in which it came together. A very soft example of a carbon solid would be that of graphite, which is so soft that you can write with it. It's what's in your pencils, so that's going to be eliminated. Consists of positive and negative ions, strongly attracted to each other. Diamonds are only carbon, so we do not have positive and negative ions. Are giant molecules in which each atom forms a strong covalent bond with all of its neighboring atoms. It is carbon bonding with carbon. They are going to be forming very strong, very non-polar covalent bonds with all of their neighboring atoms. So that sounds good so far. Are formed under extreme conditions of temperature and pressure. This isn't why it's hard. It doesn't explain the actual molecular structure of why it's hard. That is the condition in which diamonds are created. That is true. But it doesn't actually explain why it creates such hard structures. Contain orbitals or bands of delocalized electrons that do not belong to a single atom but to the crystal as a whole. This is mostly describing a metal or a metallic bond, and that is not what is happening. Carbon is a non-metal, so C is going to be my choice because carbon can form very strong covalent bonds with all of the carbons that are surrounding it.